So, in our previous video, we introduced what forecasting was, and we're making a quantitative prediction about the value of a future random variable. And we observe information at different points in time. As you can see on this timeline, time is chopped up into discrete increments. So, we measure data either daily or monthly or weekly or quarterly, however the case may be. Could be minutes, could be hours, could be whatever. We measure that data at different points in time, and then we use some of that information to make a forecast for the next period. So we introduced what was called the naive model. This is the easiest way to make a forecast, and the naive model, my forecast for today, that's time t, is exactly the same as period t minus 1, which is yesterday. So I take the forecast yt hat, which you can see on this timeline, and even though I've observed a bunch of data prior to t minus 1, I just use the data from t minus 1 to predict yt. So I may have observed t minus 2, t minus 3, t minus 4, but I only use the data from t minus 1 to forecast yt hat. And it's not sophisticated. I'm just using a small amount of information, and you can see that I did that here with these ExxonMobil stock prices. So the second column represents the closing price of ExxonMobil on the given day in January of this year. And you can see that the stock price is hovering from 69 to 70. On January 2, it closed at 70.9, so I immediately make a forecast for January 3 of 70.9. On January 3, it closed at 70.33, and I immediately forecast for January 6th. Remember, the 4th and the 5th, those are weekends. The stock market is closed. I immediately forecast 70.33 for January 6th. And on January 6th is 70.87. That data is the forecast for January 7th. So I just go back one period, I grab the data, and I make a forecast. And you can see the errors were off by anywhere from 10 cents to a little over $1, and we have percent errors that range from almost nothing to a percent or two. And so this model tends to work pretty well for stock prices if we don't have any information about what tomorrow will bring. Today is as good as the next. It is not as good of a model for predicting something like sales data. So let's try to use the same sales model, or same model of forecasting, the naive model, and let's just predict sales for the Gap in the early 2000s. So these are their actual sales. Now, this is almost 20 years ago, so revenues have gone up for the Gap since then. However, the pattern of forecasting is largely the same. And let's just take a look at the data. I have data here for 13 periods, all of 2000, all of 2001, and all of 2002, and then I have an additional period of Q1 of 2003. And you can see that sales are trending up over time. If you look at Q1 of 2000, it is smaller than Q1 of 2001, and is smaller than, and then Q1 of 2002 is a little bit smaller. Then if you look at the Q2s, those are trending up a little bit. If you look at the Q3s, trending up a little bit, and if you look at Q4, there's a little bit of positive trend there. Let's have a look at the naive forecast. So my prediction for Q2 of 2000, just applying the naive model, the data are quarterly, so the information that I use is Q1 of 2000. So I predict 2731990, or I think this is in thousands, so it's like 2.7 billion in sales. And the data is 2947714. So we missed by about 7%. And then I go ahead and use Q2 to predict Q3, and we missed by 13%. Then I use Q3 to predict Q4, and I miss by a whopping 25%. And then I use Q4 to predict Q1, and I overshoot. You can see that these forecast error is minus 1399432. That's about half of the total Q1 sales from 2000 is what we missed by. This is just an error. It doesn't seem like the naive forecast is doing very well. We're seeing these large percent errors. And what the naive model cannot do is it can't deal with the trend. It can't deal with what is clearly seasonality in this data set. So if you think about sales, January through March, we're paying off our credit card bills from October through December of the previous year. So we go and spend a lot of money on Christmas gifts, trying to keep up with social norms, dealing with our families and friends and assorted relatives that we're feeling the pressure to buy gifts for. We go ahead, we buy all those gifts, and then quarter one turns around and we don't have any money to buy any more gifts. And this is seasonal. So if you look from 2000 to 2001, you see this huge miss. From 2001 to 2002, you see another huge miss. From 2002 to 2003, you see another huge miss. I mean, this is predictable on a yearly basis. And conversely, using July through September to try to predict October through December is equally futile. So people aren't really thinking about Christmas shopping on Labor Day, but Halloween, Thanksgiving comes around and people are starting to stock up and get panicked. And then the day after Thanksgiving is Black Friday and people are out shopping. And so we have these huge misses in quarters 4 and quarter 1. And we also are losing a little bit of the variation between quarter 2 and quarter 3. So sales are starting to tick up as the year progresses. We don't capture any of that. And so the naive model doesn't seem to work very well here. And you can just see, here's the data. The data are trending up just a little bit. You can trace just a little bit of increase here. But we have this defined peaks, quarter 4 of 2000, quarter 4 of 2001, quarter 4 of 2002. And we have these defined valleys, quarter 1 of 2001. Quarter 1 of 2000, quarter 1 of 2002, quarter 1 of 2003. So there is a pattern to this data. There's a little bit of upward trend, and there's seasonality in the data, and the naive model doesn't capture any of that. So what can we do instead? What can we do instead? And what I want us to think about in this forecasting portion of class is that we have as much flexibility as we want to make a forecast. So let's go back to the forecasting timeline that we see here. I'm in time t. Let's say we just have high, low data. So it's either good or it's bad. Let's say time t is a bad period. Time t minus 1 is a good period. Time t minus 2 is a bad period. What would be helpful for me is to use information from t minus 2 to predict t. They're both bad periods. And by bad, we just mean low demand for a product, something like that. Time t minus 1 is a good period. So you can think of this as a restaurant that makes all of its money on Friday and Saturday, and then Sunday through Thursday is kind of a downtime. It's a bad time. I want to use information from t minus 2 to predict t. I'm not so keen on t minus 1. I'm not as keen on t minus 1. I'm allowed to do this. So with forecasting, you're allowed to pick and choose any information off the timeline that you think is relevant to predict time t. I don't have to use t minus 1. I don't have to use t minus 2. I don't have to use t minus 3. I can use anything that I think will represent the data generating process. So let's go back here. I'm not required to use quarter 1 of 2000 to predict quarter 2 of 2000 at all, nor am I required to use quarter 4 of 2000 to predict quarter 1 of 2001. And you might think that indeed I don't want to use quarter 4 of 2000 to predict quarter 1 of 2001. This huge miss is something I want to avoid. I'm missing by almost 50% here. If you think of throwing darts, not only am I missing the dartboard, but I'm arguably throwing in the wrong direction. So the dartboard is straight ahead of me, and I'm thinking about taking a left-hand turn and throwing to the wall that's not anywhere near the dartboard. I want to avoid doing this type of forecasting, and the naive model won't get me here with the seasonal data. Fortunately, I'm not limited, and I can use what's called the modified naive model. So instead of just using t minus 1 to predict t, I can go back in the past as far as I want and pick a period that may more appropriately represent the seasonality. And you could just think of this as being something that you could do as easily for forecasting monthly temperatures, forecasting monthly precipitation. Obviously, I want to try to match March to March. I don't want to try to match February of this year to March, nor do I want to necessarily match January to March. I want to go all the way back, maybe even 12 periods, and match last March to this March. And we're going to do that with the modified naive model. So what I'm going to propose we do here, and if you look at this bottom bullet point, I propose we use t minus 4. I propose we go back an entire year, and that our forecast for quarter 1 of 2001 is actually just quarter 1 of 2000. And I want us to look at the percent error. Before we had a 44% error. Let's try this out. Now we have a 14% error. I went all the way back 4 periods. Instead of using 4579088 to predict quarter 1, I use 2731990. I go back 4 periods on the timeline. And now with the modified naive model, you are going to be unable to make as many forecasts as you would for the naive model, but maybe that doesn't matter. So what's worse, no forecast or a bad forecast? Well, that's debatable. Probably no forecast is better than a bad one. We're making better quality forecast. If you look at these percent errors all the way through here, they're much smaller percent errors, and that's a goal that we have. So with forecasting, unlike maybe hypothesis testing where we're vested in sampling, invested in a process, with forecasting we want to model the process as accurately as possible. And we don't have some threshold or requirements on what we use to make the forecast. So this is, in some ways, it's atheoretical. In other ways, it's very theoretical, kind of the structure of making the forecast. Okay, so let's take a visual comparison of the forecast. The blue line represents the modified naive forecast, and the red line represents the data. And as you can take a look at the blue line, it mirrors the red line. Not exactly, but it's in the ballpark. And then if you take a look at the green line, that represents the naive forecast. And the naive forecast is basically choosing its own adventure here. It has no semblance of similarity to the blue line or the red line. So the naive forecast is doing its own thing relative to the gap sales. So how do we decide which forecasting technique is best? We've so far just learned 2 forecasting methods, the naive and the modified naive. We have some different techniques to evaluate the quality of the forecast. I'm going to present 3 of them to you here. The first is just looking at the percent error. I make them all positive. I calculate what's called the mean absolute percent error. Take all the percentage errors and make them positive. So I go back to this slide here and I put plus signs all the way down column 5. So the minus 2.44 becomes plus, minus becomes plus, minus becomes plus, and they're all positive. Then I just average them all together. That's called the mean absolute percent error. That is a method of evaluating the quality of the forecast. You can think of this as being more linear. What we like in this class is to do something that is very similar to how we evaluated the quality of the regression line and calculate what's called the mean squared error. And wait for it, guys. You take the errors, you square them, and you average them together. And we do this because we want to penalize really imprecise forecasts. And so especially bad forecasts get penalized with this squared term. If you square a large miss, it gets an even larger miss. And we evaluate the quality of the forecast with this mean squared error. So let's find the mean squared error for the ExxonMobil data where we use the naive forecast back here. So we're going to take these forecast errors in column 4 and we're going to square them for column 5. So I take each forecast error that I have here and I just square it. So minus 0.57 is calculated. I take the close price minus the forecast. That's how I get the minus 0.57. And then I square it for this error right here. And I do the same thing here. I take the closing price, 70.87. I subtract 70.33, and I get 0.54. And I square it here. And you square all the way down. Now, I want to highlight something here. Take a look at the January 8th. That was the worst miss that we had. The forecast error is maybe double the size of the next highest. Maybe not quite. It's not quite double 0.66, but you can look at the squared error. It's almost 2.5 times. So it really penalizes this particular miss. And if you look at the sum of the squared errors, when you add all of these up, you get 3.6584. That's all 9 of these squared errors. A bulk of that is coming right out of this miss. Now we divide by 9, that gives us the mean squared error, and what we use to evaluate the quality of forecasting is the root mean squared error. And you think of the root mean squared error as just being kind of a, what do we think the average miss looks like? And we're controlling for especially large misses here. So the root mean squared error, this 0.6376, is kind of giving us a barometer of what we might expect a miss to look like with this particular forecasting method. So you can see a number of these errors are smaller than 0.6376, but we do have a couple that are larger, and it is influenced heavily by this minus 1.06. So bottom line, we use the root mean squared error, where we square the errors. That's the squared term right here. We divide by the number of forecasts that we make. N is the number of forecasts, and we just take the square root.